Good morning, students. Today, in this lecture, we will discuss about the color image processing. So, before starting the color image processing, we will discuss about the basic fundamental of our color signals. So, if we are talking about the color image processing, so there are two categories of the color image processing. First one is called as a full color image processing. So, in images are acquired using a full color sensors. So, these are applicable to the color TV cameras or color scanner. Second one is the pseudo color image processing. So, assigns a color to a particular monochrome intensity or a range of intensity. So basically, use of color in image processing is motivated by two principal factors. So first one is the color is a powerful descriptor that often simplifies the object identification and extraction from a scene. Human can discern thousands of color shades and intensities compared to about the only 2 dozen shades of gray. So if you are talking about the monochrome TV or so on, so there are only a if you are talking about the gray level, so there are only 2 dozens of shades in our gray level system. But when we are talking about the color shades and intensity, so they are basically color shades are in the range of the thousands of ranges. So it is a much difference between the gray shades and the color shades. Second factor is particularly important in manual image analysis. So that is basically when performed by the human. So now first of all we will discuss about the color image processing. So that is as we have to already seen in divided into the two parts. Now in second category the problem is one of the assigning a color to a monochrome intensity or range of intensities, and some of the grayscale methods are directly applicable to the color images, and other requires reformulation to be consistent with the properties of the color spaces. So, first one we will see that the process followed by a human brain in perceiving and interpreting the color is a physio and psychological phenomena. So, it is not yet fully understood, but the physical nature of color can be expressed on a formal basis supported by experimental and theoretical results. So, what will occur when a beam of sunlight passes through a glass prism? The emerging beam of light is not white, but it consists of a continuous spectrum of colors ranging from violet to red. So, you can see here, we have to also study about this in our previous classes. Ki what will happens when a white light will crosses through the prism. So that is basically a optical prism, and the color spectrum may be divided into the six broad regions. So what are the broad regions of the color spectrum? That is the violet, blue, green, yellow, orange, and red. So if any white light is crossing through the prism, so according to different wavelengths of their light, so that will be the spread it into the output side of the second layer of our prism. Now that is the spectrum. So that is a various spectrum. According to wavelength, we can see the visible range of our. These are the broad range of our color spectrum. So by using this spectrum, we can see that there is also a red, green, and blue part. So we can see that no color in the spectrum ends abruptly, but rather each color blends smoothly into the next one. So means there is a different shades. If we are turning to the red part and moving to the green, so there may be some intermediate color also in between these two colors. So we can also see what about the basic fundamental color theory, in which by how we can generate the different colors by using. So here we can see that no one color is ends suddenly. They may smoothly they will mix to the next color. So in between the intermediate part of these two colors, RBG colors, so there may be a different shades will be generated here. Basically, the colors that we perceive in an object are determined by the nature of light reflected from the object. So what about we have to previously study that if there is a object and it will be perceived a particular color of that object, so that is the basically nature of the light reflected from the object, means that is the property of that particular object, that it will be reflected that particular color, and remaining color it will be the objects. So body that reflects the light that is balanced in all visible wavelengths appear white to observe. However, a body that favors reflectance in a limited range of visible spectrum exhibits some sets of the colors. So that is basically also depend on the reflectance property. So now you can see what will happens if we have a illumination source, and these are the basically these rays are incident on the particular object, that is the basically tree. So since the property of tree is that it will reflect the green color and it will absorb the all other colors, so according to that, that tree will illuminate just like a green shade. So that is the reason ki why we have to see any type of color in that particular part. Now we will again see there what about the intensity, and what about the intensity is a weighted function. You can also assume that red color has a its own intensity, green color has its own intensity, and blue color has its own intensity. So now what will happens, that is basically intensity is a weighted function. So that is the, and what about the weighted function, so that is a weighted into the RGB. So that is a red, green and blue colors. So if we have to measure the intensity, so I doesn't weight each component identically. So what will happen? Intensity is equal to the 0.299 red, 0.587 into green plus 0.144 blue. So that is assumes three light sources have the same actual intensity but are colored red, green, and blue. So that is basically we have to see that three light sources have same intensity, but they are different colors. So that is basically we have to if we have to just the white light, so there may be some. So just suppose green objects. Okay, so we can start from the green objects reflect the light with wavelengths primarily in the range of 500 to 570 nanometer range, while absorbing most of energy at other wavelengths. So what will happen there, if we are talking about the green object, so there is a property of green object that it will reflect the light. So what is the range of wavelength range? That is a 500 to 570 nanometer range, while absorbing most of the energy other wavelength. So that is the reason why green objects are looking like a green, because it will reflect the green colors and it will absorb the energy of other wavelengths. The characterization of light is central to the science of the color. So what about the basic characteristics? If the light is a achromatic, its only attribute is its intensity or amount. And chromatic light spans the electromagnetic spectrum from approximately 400 to 700 nanometer. So that is basically we have to describe about this one. What about the chromatic light? So that is a basic range of our chromatic light is the 400 to 700 nanometer. The three basic quantities are used to describe the chromatic light. So what about that quantity? So that quantity is the radiance. First parameter is the radiance, second parameter is the luminance, and third one is the brightness. So we will see what about the radiance. So radiance is the total amount of energy that flow from the light source, and it is usually measured in the watt. So that Now, second one is the luminance. So, measured in lumens, gives a measure of amount of energy an observer perceives from a light source. So, that is basically a actual color of that particular object. Now, if we are talking about the light emitted from a source operating in the far infrared region of the spectrum could have sufficient energy, means radiance, but an observer would hardly perceive it. Its luminance would be almost zero. So if you cannot perceive that particular, so that will be the almost zero. Finally, brightness is a subjective descriptor that is practically impossible to measure. So if we are talking about the brightness, but it embodies the achromatic notion of intensity and is one of the key factors in describing the color sensation. So now here we have assumed the cones. So what about the cones? Cones are the sensors in the eye responsible for color vision. So we can also see that there are a different sensors. So in our eyes there is also a sensor that is called as a cones, and it will sense the color vision. And if we are talking 6 to 7 million cones in the human eye, okay, so if we are talking about the human eye, so in human eye there are 6 to 7 million cones in the human eye, can divide it into the three principal sensory category and corresponding, so that is the red, green and blue. So all these cones are divided into the three major categories. Approximately 65% of all cones are sensitive to red light, 33% are sensitive to green light, and only 2% are sensitive to blue light. So there is a just classification. The major part of the cones are sensitive to the red light, and blue cones are the most sensitive cones. So that is the basically. And now we have to see this graph. In this graph we can see that the basically spectrum. So absorption of light by the red, green and blue cones in the human eye as a function of the wavelengths. So these are the different wavelengths, and according to that, blue, green and red, these are the spectrum of these three colors, and absorption of light by these colors are basically human eye as a function of the wavelength we can judge it. Now what will happen here? So due to these absorption characteristics of the human eye, colors are variable combinations. Okay. So these combinations are primary colors, red, green and blue. So we are talking about the three primary colors, that is the red, green and blue. And these are the due to absorption characteristics of the human eye. Colors are variable combinations. So it will be different combinations. So we will again discuss in further. So for the purpose of standardization, the CIE, International Commission of Illumination, designated the specific wavelength value. So if you are talking about the particular wavelength value of RGB, so wavelength of blue, that is 435.23 nanometer, green 546.1 nanometer and red 700 nanometer. So these are the particular wavelength, but having three specific primary color wavelengths for the purpose of standardization doesn't mean that these three fixed RGB components acting alone can generate all spectrum colors. So the primary colors can be added to produce the secondary colors of light. So that is basically RGB is the primary colors, and we can make the secondary color, that is the magenta, that will made by addition of red plus blue, cyan, that is green plus blue, and yellow, red plus green. So that is a by combination or addition of two colors, a new secondary color will be generated. Now we will see that mixing of three primaries or a secondary with its opposite primary in the right intensity produces the white light. So if you have either mixing of the three primary colors or a secondary with its opposite primary color, so that produces the white light. So I mean basically, if we are talking about the white light, so that is a basically mixing of the red, green and blue in proper weightage. So in this diagram, you can see here when we have to mix the red and green, so there may be generation of yellow color. When we mix the red and blue, so there is a generation of magenta. And when we mix blue and green, so there is a generation of cyan color. So and all three colors when we have to mix, that is the white color. So now here we will see what about the color additive theory, and is a fundamental component of color additive theory must be understand how we can add these colors. So that is art, digital and design field. So there are different places we have to know about the proper color theory. So if we are talking about the red, blue and green, so these are the primary colors, okay, and mixed together and perceived by the human eye. So, and by combination of these three colors we can make a different colors. So we are going to go over an in-depth definition of color additive theory to gain a solid understanding of its importance in the those fields. It is a subtractive mixing. So in subtractive mixing, you can see that we have to use the magenta, cyan, and yellow color. So that are the our secondary colors, and by two secondary colors will make a primary color. Primary color. Suppose cyan and magenta, that will added, and that will make a blue. Cyan and yellow make a green. Magenta and yellow make a red color. And by when we have to subtract all these three colors, that will make a black color. So these are the subtractive mixing theory of our color fundamental. The color additive theory is defined as the how the color are mixing the primary colors red, green, and blue, and how these mixed colors are perceived. So that is the red, blue, and yellow are so make these colors. So as but in color additive theory, the primary colors are RGB. Now you can see both the what is the difference between these two. One is the additive color mixing and another one is the subtractive color mixing. So in this diagram, we can see that white light is combination of red, blue and green. Okay. So by making the three primary colors, white color will be generated. When equal parts of red, blue and green bands are added to one another, white light is created, and that is the basis of additive color. When all three additive colors are removed, black is perceived. Okay, so that is basically when all three additive colors removed, then black is perceived. On the other hand, when different primary additive colors are combined, brighter colors are created. So there is also a different primary additive colors we can combine, then brighter colors are created. So we can see that there is a certain different shades are generated by different proportions of these colors are added, and due to this we have to get the different shades in different colors. Color television perception is an example of additive nature of the light color. So that is basically the color television reception is a basically the perfect example of additive nature of color. So in color television we have to use the color mixing, additive color mixing. A primary color is defined as one that subtract or absorbs a primary color of light and reflect or transmit the other two. Now, the primary colors of pigments are magenta, cyan, and yellow, and the secondary colors are red, green, and blue. So, this is the subtractive color theory, and a proper combination of three pigments, primaries or secondary, with its opposite primary produces the black color. So that is basically the things what we have to discuss. The characteristics generally used to distinguish one color from another. So how you can distinguish between the two colors? So there is a certain rules in which we have to see that the color from different from another color due to their brightness, hue, and saturation. So brightness embodies the chromatic notation of the intensity. So what about the intensity of that color? So that is known as the brightness of that particular color. And hue, what about the hue? Hue is an attribute associated with the dominant wavelength in the mixture of the light waves. And hue is the basically represents the dominant color as perceived by an observer. So basically, what if we are seeing the red tomato? So that is the hue of that tomato is the red. So that is the reason behind this. Now we will see that thus when we call an object red, orange, or yellow, we are specifying its hue. So what is the hue? Hue is the actual color. What color it will be reflected, and we will observe that particular object. That is the hue of that object. The pure spectrum colors are fully saturated. The colors such as pink, lavender, violet, and white are less saturated, with the degree of saturation being inversely proportional to the amount of white light added. So that is the reason if colors pink, if you want to generate a pink, so that is a combination of red and white. Lavender, that is a violet and white, are less saturated, with the degree of saturation being inversely proportional to amount of white light. Hue and saturation taken together are called chromaticity, and therefore a color may be characterized by its brightness and chromaticity. So, if you are talking about the hue, what about the hue and saturation? So, both are the part of our chromaticity. The amount of red, green, and blue needed to form any color are tri-stimulus values and are denoted by the X, Y, Z respectively. So, that is the value. A color is then specified by trichromatic coefficients. So that is small x, that is equal to capital X upon x plus y plus z. Small y, that is equal to capital Y upon x plus y plus z, and small z, that is equal to z upon x plus y plus z. So it is noted from these equations that small x plus y plus z, that is equal to 1. So that is a color is specified by trichromatic coefficients. And another approach for specifying the colors is to use the CIE chromaticity diagram, and which shows color composition as a function of X and Y. So that is basically we will discuss about the what about the color chromaticity diagram. And in color chromaticity diagram, we can see the different shades of our primary colors. So this is our chromaticity diagram. So red, blue, and green, and we can see here the different shades of these three primary colors. So what about the chromaticity diagram? So you can see here, this is a vector from that particular. There is also a different shades. So there are three primary colors, RGB. So according to that, we have to see that in between the red and green, there are different shades of that particular combinations. If you are going towards the green color, so there are the shades of green, and if you are moving towards the red color, there are shades of the red. Same thing is here, nearby blue mixing with green, so there is a green blue shades. If we have to move towards the red part, so there is a violet shade, and in center there is a white color. So you can see this is the wavelength ranges which we have to see here. You can also see bluish green, green, bluish green, greenish blue, blue, purple, purplish, purplish red, reddish purple, purple's pink. So that is a different minor shifting from blue to green, green to blue. There may be different shades are generated by the color theory. So this is the basically you can see here. This is a 530 green color. This is a wavelength of green color. There is a 400 nanometer wavelength of blue color, and this is a 700 to 740 nanometer. This is a wavelength of red color. And according to different by the additive color mixing, we can generate the different colors. So now we will see that the positions of the various spectrum colors from violet at 380 nanometer to red at 780 nanometers are indicated around the boundary of the tongue-shaped chromaticity diagram. So basically, we can see that the positions of the various color of. So we have to see the violet to red. So there are different shades are shown in our chromaticity diagram. So for any value of x and y, the corresponding value of z, that is equal to 1 minus x plus y. So the point marked green in the figure, for example, has approximately 62% green and 25% red content. So from above equation, the composition of blue is approximately 13%. So you can see in here. The chromaticity diagram is useful for color mixing because a straight line segment joining any two points in the diagram defines all the different color variations that can be obtained by combining these two colors additively. So basically, we are opting the additive color theory, and that is the color mixing part. We can see that extension of this processor to three colors is the straightforward. So to determine the range of colors that can be obtained from any three given colors in the chromaticity diagram, we simply draw connecting the lines to each of the three color points. So there may be how you can define the range of colors. So the result is a triangle, and any color inside the triangle can be produced by various combination of three initial currents. So triangle in the next figure shows a typical range of colors processed by the RGB monitors. The irregular region inside the triangle is representative of color gamut of today's high quality of color printing devices. You can see here colors perceived by the human eyes, printable colors, colors that can be displayed on RGB monitor. So there is a different ranges in which we are working. Now we will see about the little bit focused on the image part also. So what about the color and images? So you can see here, this is a structure of a digital image pixel, the color of an image at a specified point. Sample one dimensional of a pixel, band all samples on the same layer. So we can see here is a red, green and blue layers one by one. It can arranged. Now there is a image types, binary image, grayscale and color. If we are talking about the binary image, so there is exactly two colors. It is defined by grayscale has no chromatic content. That is based on the black and white. Color contains some pixels with colors. More than two colors exist. So if we are talking about the colors, so here is a more than two colors that exist. Now we will see here application of additive nature of the light color. So what about the nature of light and what is the additive color? So you can see this is the color TV, red, green and blue. These are the three shades of color and these are the color monitor and RGB. These are the different colors pattern. Now conversion of color to a grayscale image. So color image can be converted to the grayscale. Okay, so we can also convert our image onto the grayscale by replacing the RGB value by luminance value. Okay, so what about the luminance? So it can be obtained as a gamma that y that is equal to RGB plus 3. So that is the average value of our color. So but image obtained by this method is too dark in the red areas and too bright in the blue areas. So this average method conversion of color to grayscale is not very good. So now we will also of the RGB to gray. So to remove this, we adopt a method using the weights. There is a certain weight according to which we cannot take the equal amount of RGB. We will give the separate priorities to these colors. So that is a 0.212, 0.7154 and 0.072. So these are the weightage which we have to given the different primary colors. So WR that is the 0.2125. So that is the weightage of our red color. WG 0.7154 weightage of green color and WB 0.072 that is the blue color weightage of our blue color. So this is the method. Similarly, desaturation is a process of removing the RGB in the linear manner. So you can see here k is the lies between the 0 and 1. So what about the we have to generate the R dash, G dash and B dash. So this is the formula for generating. You have to given the luminance and according to that you can calculate the value of this. What about the color distance? Okay, so there is also a method for calculating the color distances. So quantifying the difference or similarities between the two colors. So how you can calculate the similarities between two colors? Okay, so L1 metric is the taxi cab distance, L2 metric is the straight line distance. So distances are often normalized to the interval 0 to 1. Compute the distance in normalized color space. Divide by maximum possible distance in that space. So this is the method. What about the L1 and what about the L2? So we can see in this diagram how we can measure the distance L1 and L2, and that will show the basic similarities of between the two colors. So color depth. What about the depth? So ability of an image to accurately reproduce colors. So given as the number of bits consumed by the single pixel and otherwise known as the BPS, bits per pixel. So according to that we can measure the depth. So binary images are BPP, means number of bits per pixel. Grayscale images are typically BPP and color images are, so we have to here just see what number of BPP we have to require for describing these scales. So just you can see if A is the 1 BPP, here is only black and white. 2 BP, there are 4 levels of colors which we can represent it. Again, you have to increase the 5. So if you have increased the 5, so there is a number of levels are less but sufficient. But when you have to increase the number of BPP 24, so there is a very fine representation of our picture, because you can accurately define the every colors, every shades in your images. So that is the role of our BPP or defining the color. So what about the color standardization? So we will see. So that is basically how CIE has standardized specific wavelength to the three primary colors. So if we are talking about the blue color, so that is the 435.8 nanometer. And if we are talking about the green color, so that is a 546.1 nanometer. And if we are talking about the red color, so that is a 700 nanometer. So these three colors mixed in different intensity proportions can produce all visible colors. Wavelength also needs to be varied to produce all range of visible colors. So here we have to characterize our color. So brightness. So it embodies the achromatic notation of intensity. So one color can distinguish from others. So what about the brightness? So first factor will be the brightness. So it embodies the achromatic notion of intensity, hue, dominant color, wavelength of the light as perceived by the observer. So that is the hue is the basic original color which is observed by the observer. Saturation, that is a relative impurity or amount of white light mixed with a hue. So that is basically the saturation. So these are our the very basic model of our color theory. We can define this, how we can distinguish between two colors. So we have to know the brightness, because these brightness part is a very important role when we represent any color image into the grayscale level. So these, according to these brightness party, we can calculate the what about the gray level of that particular, because the gray level is directly related to the brightness of that particular image. And if you are talking about the hue, so hue is the original color. So it is also depend on the wavelength of that particular signals. And saturation, so that is a how much amount of white light you have to add it. So if you want to go to the very light shade of any colors, so means that the quantity of white light is more in the color, so that is the shades of that color will be very light in that particular part. So before starting the objective question, so we have to again see that what is the basic color theory in which we have to use. And so there are two three factors we have to more remember. One BP. So what is the role of color and bits per pixel? So that is the basically the difference ki when we have to increase the bits per pixel, there is a large number of levels. So what is the role of large number of levels with respect to colors? So these levels are the basically shades of our different colors. And due to these colors, so these color is responsible for enhancing the image quality, image perception or visual basic enhance the vision of our image, quality of our signals. So actual visibility of signals will be increased, good quality will be increased by enhancing the number of bits. Because when we enhance, suppose we are taking the 24 bpp, itne bits per pixel. So you have to, so how much amount of levels you have to acquire? 2 to the power 24 levels you have to acquire. And there are a large number of levels. So 2 to the power 24 levels means you have a such amount of shades of color for representing your image. So this is a very important parameter, how number of bits we are using for representing the pixel. And as our levels are low, there maybe the image is moving towards the black and white part. So that's all from my side. Up now we will see the color model. So what about the color model is also named as. So what is the name of our? So you have to see about what do you mean by the term pixel depth. So how you can measure the pixel depth and what is the basic name we have to use for the depth of a pixel. How many bits RGB color image is represented by full color image. So there how which bit will we have to use for color image format. So there is a fixed format of color to completely study about these the basic part, and then we can attempt the objective question. So I think you will be much better. So what is the equation used to obtain the S component of each RGB pixel in RGB color format? So what is the basic equations? Now next one is the what is the equation used to obtain component of each RGB pixel in RGB color format. So what is the method for achieving this? Now what is the equation used for calculating B value in terms of HSI components? So you can also use this one. So which of the following color models are used for color printing? So you have to know about the which model we are working on the color printing. So now this is our objective question. So at last we have to again conclude that part about the color fundamental theory. So that is the most related theory in which we have to understand what is the relation between pixels and color theory. If you have how you have to work out, what about the basic components which we have to using in color theory, what about the gray scale, how we can use the gray scale. So that is basically again we want to explain you that if we are working on the color signals and our each image is represented in a color format. So if your signal is a color signal, means your signal is basically made of combination of RGB or any weighted factor of RGB. So how you can represent if you have don't have any type of color is because you have to assume that your picture tube, your receiver part, monitor will be a color reception, because if you are talking about the color television, so there is screen, so that is the made, so that is acceptable, so that screen is designed for accepting the color signal, because according to signal that screen may be illuminated according to different shades of color. So if your screen is designed in such a way that it will implement the different color signals, but if your screen is black and white and your signal is color, then what will happen here? So according to the luminance part, what about the brightness section of that your color signal? So according to that brightness of your color signals, that will be reflected or converted into the grayscale part. Okay, and that particular all complete color signals will be converted into the basic part of all will be converted into our shaded part, grayscale. So that is a percentage of grayscale according to intensity of your signals. So that is the compatibility. If you have a color signals and you don't have a monitor, color monitor, you have a black and white monitor, so that signal may be converted into the black and white picture. And there is again a option, if you have a black and white signals, you don't have a color signals, but you have a color monitor, color receiver. So how you can adjust this? So there may be compatibility कि a black and white signals will be easily converted into the screen of, because our screen is made of different pixels. If we are working on the color signals, our complete pixel is divided into the RGB, red, green, and blue, and according to that, they illuminate. So that signal may be again converted into the brightness part, and according to that signal's brightness, our screen will be compatible with the black and white signal. So that is the reasons which we have to you. So you have to know about the gray signals and the color signals. So there may be a compatibility. Whatever the signals you have, according to your screen, that signal will be converted into the another format. So this is the base of our compatibility of in color theory sections. So okay, I think it will clear to you. What about the basic fundamental of our color theory? In our next lecture, we will discuss about the enhanced processing in our color theory concept.